so the main goal here is that we would like you, like especially the people, if you use Lumi, that you can. So we did some changes to the exercises, and so you would need to do this git pull again. So I wanted to briefly show this. So this some of this, of course, maps quite well to your own machine also, if you don't use Lumi. But what we want to do is we would like to log into the Lumi web interface, and then we would go to this login node shell. So I did that already. And then basically what we do is that we go to the location or the folder where you have saved your repository. So in this case, it's this. For me, it's this intro. Let's see. How's it called? Deep learning intro. Of course, it's the other way around. And then we would just go here and do a git pull here. And then, so for me, it says already up to date because, well, I did this like earlier, but this would be the way so that you make sure that everybody has the up to date notebooks. And then, of course, the next step would then be, and I'm not going to show this in detail, but if you want to use also today, again, the Jupyter notebooks on Lumi, you would go here to Jupyter, and then we would have, as you know from the last days, again, this ability to use this reservation, and then you can launch a job there. And the reason I'm showing that is because Ludovico is using his own machine. So that's of course also still an option. I guess noteworthy, like for today, is that some of this stuff might take a little bit longer depending where you run it, right? So especially I think the later sessions or already in the first session actually we do a lot of training, so that might take a bit longer. But yeah, so just so that you've seen this, and then I think now we could um, perhaps move to the actual session.
Okay, perfect. So then let's get started. So what we've seen in the last today is that we can build deep learning models by stringing together a lot of these neurons that we've seen in the first day, where each neuron takes a bunch of inputs and combines them together to produce an output. And we've seen that we can actually build quite powerful neural networks by stringing together these into layers and then putting multiple layers on top of each other, forming these, we could say, this deep hierarchy of layers, which is where the term deep learning comes from, right? A deep neural network is deep because it has many of these layers on top of each other, with each layer formed by many, many neurons. And until now, what we've seen is that we've seen situations where every neuron in a layer can see all the inputs coming from the previous layers and compute an output on all of those. So we've seen these fully connected layers. And those are good when you want to work with, let's say, tabular data, like we did until now. But and this is, I think, a joke that I put in HackMD also yesterday. There used to be a guy on Twitter, back when it was called like that, who used to take any paper that used the fully connected layers to work on tabular data and beat it by using approaches that are not in deep learning, by using mostly XGBoost. And his point was just that, hey, you don't need deep learning for everything. And he was quite successful at this. But one key point that I want you to understand today is that the real power of deep learning comes from the flexibility that this neuron architecture gives us, by the fact that we can actually string together neurons in a lot of different ways that are optimized for different tasks. And this allows us to very easily build a deep learning model that can process data that is not tabular, like the ones we've seen yesterday, data that comes in other shapes and forms, of which there is a lot. I mentioned just one moment ago in the icebreaker that I like to work with graph data. Graphs are not tabular structures. You can't just process them through a fully connected layer. It will not really work. But we can build specific deep learning models where the neurons are arranged in a way that work well on graphs. And similarly, with images, how do we process an image with a neural network? Well, we have specific layers for doing that. And this applies to a variety of different types and shapes of data. I don't know, Marlon, if you have any other types of or shapes of data in mind that do not really work that well as tabular data.
So I would just maybe, for example, so you talked a lot about images. I guess text is another way where like, text can be of arbitrary length. So um, well, I think that's quite obvious statement. So whereas like, I guess tabular data is usually very defined in certain schema. So text would be the first thing that comes to mind for me.
Yeah, that is a very good point. And that's very easy to see that when you have a variable length, you cannot really use a traditional neuron architecture to work with that. Uh, Audio, I actually think, is another very interesting example where how do you process an arbitrary length audio or an arbitrary length time series of any kind, where you have a bunch of measurements taken over time. So these are all cases where we actually can build and we know how to build deep learning architectures for that, stringing together neurons in a way that is designed for the specific structure of the data. And today we're going to do this with the images as an example. So as usual, the first point for us will be to formulate what is the problem we are trying to solve. That's always the first step. And what we will do today is that we will try to do image classification. And we will use a data set called Dollar Street, and specifically a subset of it that you can download from the link here in the lesson. It's already downloaded for you if you're on Lumi. If you're running locally, you can just click on this link. It will bring you to a page that looks a little bit like this. It's very zoomed out here, but if you scroll down to the list of files, there is a list of files down here, and if you don't have it too much zoomed in, there will be a button called Download All, where you can download a zip file containing all the data that we will need for today's lecture. And then you can unzip it in a folder on your machine. Again, if you're on Lumi, this has already been done for you, so you don't have to do it. And we can load this dataset, and the dataset comes in 4 files that are in the NumPy format, so we can use the NumPy library to directly load them. So we have images for train and test splits and labels. So this data is already split for us. And if we go and have a look a little bit at what is in this dataset, well, this is a dataset that contains images crowdsourced through people on the internet. And each image is categorized. And in this specific sample, we have 10 different categories of common everyday objects. And these are examples of the pictures that we have in the dataset. And well, let me just say that these images are not great. For example, if these up here are running shoes, well, then I think we have some sort of problem. And this actually brings an interesting point for a real-world deep learning, which is real data is very, very messy. Very, very messy. So data never really matches what you would expect it to be. Like this tile roof, actually, I mean, you can barely see the roof in here. So this is quite an interesting challenge when you work with the real-world model. How do you handle this sort of data? For today, we will not really do anything about this, and we will just try to train a model that can work with this very messy data. And another point about this is that this is a classification task. We are trying to detect what is the object shown in the picture. But one thing with pictures is that they never really show a single object, right? So for example, this picture, which is marked as table lamp despite actually not having a table lamp, while it has a lamp in it, it also has a clock in it. So when we do classification here, we can't really say, well, what is the object in the picture, but maybe what we want to train the model to do is figure out what is the main prominent object displayed in the picture belonging to one of our available categories. So this is kind of the task at hand. Quite challenging. Have you seen datasets this bad, Marlon, in your experience?
I think the funny bit is if you do machine learning research, like I think if you want to do like really like big networks, then you need a lot of data, right? I've had a look at some of these. I guess also some of the data sets we look in the later lesson when it comes to transfer learning. These really big data sets, and I do have seen like quite messy ones. And I think this also brings like another question here that maybe could briefly discuss that like where are these images actually from, and can there be any problems when these images are like in some data sets and used? So what do you like? Can you say maybe something with regard to that, like kind of for example copyright or these kind of things?
That is a very good point, and it's a big problem with deep learning, especially large-scale deep learning nowadays. You need more and more data to train bigger and bigger models, and the question is always where do you get this data and how? And the good thing about this specific dataset is that these data were collected by people who knew what this data was being used for. So people volunteered images to this that they took. So it was clearly done on purpose and with the people involved knowing what was happening. But there are other datasets that instead contain images that are scraped from the internet. And when you scrape images from the internet, well, is it really something that you can do? Can you really use data that others created without their consent?
Mm.
Especially when it comes to things that, yeah, as you mentioned, might have copyright attached to them. If I produce a piece of art or creative thing, text or an image that I made, I own the copyright for that. And there are very limited things that other people can do without my permission on data that on creative outputs that I copyright. So yeah, that is a very good point and something to be very mindful of when collecting data for machine learning tasks. So do I really have the permission to do with this data what I want to do with it? And what are the consequences of me using this data? These are very, very important questions, in a sense, ethical questions attached to deep learning and machine learning more in general.
And
So
just
very good
like to
point.
briefly add to that, maybe I guess it's also not uncommon that data sets get pulled again, right? So that something gets released and then like after some while, then somebody realizes, oh, there's maybe even some problematic images in that, not only copyright but other things. So
Yeah.
it's very like highly discussed and obvious problem. Yeah. Sorry to interrupt you. I just wanted to mention
No, no,
that
no,
also.
absolutely
Yeah.
good point.
Yeah.
Absolutely good point. But then if we have downloaded this dataset and we have loaded it, let's try to quickly look at what is in it. And if we take our training images and look at the shape of these images, we get something like this. So what does this tell us? And if you remember from the last lectures, we had two numbers, right? The number of rows in our tables and then the number of features that we had. And here what is happening is something similar. What we're seeing here is that we have 878 images in our dataset. And each image has this shape, 64 by 64 by 3. What this means is that each of these images is 64 pixels tall, 64 pixels wide, And every pixel has three components, red, green, and blue, because these are color images. If we had black and white images where every pixel only had a lightness, then it would be just 64, 64 by 1. So yeah, and this is the thing, like these are not just flat sets of features. These are structured information that we have within each image. And now the small question for you is, and I will copy this into HackMD if my laptop cooperates.
I actually just already copied it to
Oh,
HackMD to the
well, then
interactive.
even better. Then it's already in HackMD, and you can go and check what is the number of features in the dataset.
For like each image, right? Yes.
Yeah, for each image, exactly. And you can write your answers down there in the HackMD document. Okay, people have been voting with pluses. And people seem to be overwhelmingly voting for option C, 12,288, which is the correct answer. Why? Because for every image, we have 64 times 64 times 3 different numerical values, because each color of each pixel is a numerical value in our image. And if we have a look at what are the values of these numerical values of these pixels, we see they range between 0 and 255. And this is quite common, with 0 representing absence of a color and 255 representing the maximum presence of a color. So for each of red, green, and blue, if we take, for example, the red component, 0 means there is no red in this particular pixel, 255 that there is a lot of red in this pixel. So if a pixel has 0 in red, green, and blue, then it's a black pixel. If it has 255 in all of red, green, and blue, it is white. If it has 255 only in the red component, then it's a red pixel. And all possible combinations of these. Of course, if we have 878 images, we also have 878 labels. And every label is just a single numerical value, which is why we don't have an extra component here. And it's a numerical value that ranges between 0 and 9 inclusive. So 10 different values that represent our 10 different classes. So now that we've looked a little bit at the data, we can now prepare it for training. And I will now be following the PyTorch version of this lesson, although there is also the Keras version available here, which for the data preparation at least is quite a lot easier. And here, if you remember in the previous lectures, we have used tensor datasets to pass the input to our data loaders. So basically, we've taken our features and labels and built tensor datasets out of it. And that is a built-in approach for tabular data. But in general, when you're working with arbitrary data, you can use your own class. You can build your own class, which will extend the basic dataset class offered by PyTorch. And this enables you to have arbitrarily code to load any sort of shape of data that you might have. And what this class must have is these two methods, getItem and len. And these are important because this is what the data loader will later use. So when the data loader takes in your dataset and builds batches for you, it will do so by using these two methods. It will use the length method to ask the dataset how many entries are in it. And then it will use the getItem method to fetch specific items to build a batch. So if data loader decides that this batch will have to contain images 5 and 15, it will call that getItem with 5 and 15 as different inputs. So if we look at what we're doing here, we are using this class to load a specific split. So we decide whether we want the test or the train split and load the correct images and labels. And one important thing that we do is that we scale this down As I mentioned, the values are between 0 and 255, but deep learning models really prefer small values, ideally around 0 and maybe spreading between -1 and 1. But between 0 and 1 is also an acceptable range for your inputs to a model. Even if they go a little bit over, it's not a big deal. But you don't want large numbers in your dataset. So here we do a very simple thing. Because we know that the values will always be between 0 and 255, and because we know that these values are quite evenly split because all kind of colors appear in the images, we just divide all these values by 255, which normalizes them between 0 and 1. So because we know a priori that 255 is the maximum, we can just do it in this way. So we don't need to use scalars like we did last time around, where we actually use the scalars that look at your data and find out how much to scale it depending on how big each feature is. Here we know they are all 0 to 255, so we can just do this division very easily. And then,
Maybe I
yeah,
can stop you already, or like I guess you wanted to go to the get item now.
yes,
Okay, then I can maybe ask afterwards. Then you can continue for now. Yeah.
absolutely. I will finish with the get item. So what we do here is that we load all the images, and then in the get item, what we do is that we load a specific image and the corresponding label. And what we do is that we convert them to PyTorch tensors. This is the same that we did in previous lessons, if you remember. But additionally, what we do is that we also perform a permutation here for the image. And what this does is that it changes the order. So we saw that the order was 64 by 64 by 3. So width, height, and then colors. We actually want the colors to be first. So from 64, 64, 3 to 3, 64, 64. And we do this because this is what is the standard expected in PyTorch. So it expects images to come with the color first and then width and height. So yes, Marlon.
Yeah, I was curious. So you said that in Keras this is maybe a little bit less complicated, and then in PyTorch it seems quite like a lot of overhead to create maybe your own data sets, a class. So I was wondering like kind of what is your
Why?
feeling on that, or what is kind of like, do you think it's really that complicated, or um give a bit maybe like if you have a new data, like is it like a huge task, this creation of the data set, or
So this looks complicated the first time you look at it, but once you grasp the basic concept, it's actually not that hard. It's not that hard to work with. And it brings some significant advantages because it allows you to very, let's say, easily customize the way the data gets loaded. So you can, for example, here we are permuting the data, but any sort of transformation that you need to do, you can do it on the fly here, which means if you have some expensive computations and something that cannot be easily stored, you can do it on the fly as it's needed. And this really gives you a lot of flexibility of, for example, loading data through a network connection, for example, once you need it, performing intensive, or let's say performing calculations that you would not want to cache because they would use too much memory. So these are all useful things that can be done in this way. And it's really, once you understand, not that hard. It just looks a little bit intimidating at first, but it's really just describing what operations to do on every single entry in your dataset. I don't know if that answers your question.
yeah, I think it's good to yeah emphasize it, that at first it looks like a huge thing, but then maybe once you have maybe trained a couple of models and used some different data sets, you actually do appreciate the fact that you can customize, as you said, but also there's like quite some data sets out there where you can also take a model from, right? So you can see, okay, for example, certain standard data sets are also implemented in, I think, in Torch Vision or in PyTorch, and then you can just see, okay, how do they do it? and then copy. So it's like at first seems quite a big thing, but then I think it's important to emphasize that this is like more or less standard, and it's just like some adaptations you need to do. And I think a lot of also, for example, if you now mentioned this permute here, I think that's something that with data, it's like always in different shapes, right? So you start training and then it crashes and then you're like, okay, I guess I need to permute or need to do some like because you work with data, it might be a bit dirty or like bit different, always in different shapes, and so I think this is just like a lot of also trying out, maybe.
Yeah.
Yeah.
And we will see later today how this can be tweaked very easily to add extra functionality into it, Marlon. So
Yes.
it's going to be very interesting. But then let's now that we have our dataset loaded, let us now look at our model. So the next step in our pipeline is always to build a model or choose an existing model to use. In this case, we will try to build our own model. So someone might say, okay, well, let's do like we did last time. Let's now build a fully connected layer. So let's just build the same architecture that we built last time around. And the question is, okay, if we want to have a layer with 100 neurons, so we want to extract 100 patterns from our images using the approaches that we used yesterday and the day before, how many parameters would a layer with 100 neurons working on our images have? And again, this is available in the HackMD.
Mhm.
And some answers are coming in, and people are correctly answering option B, 1,228,900. The reason being that we have these many input features, 12,288, and each of our 100 neurons will have to connect to each of these, resulting in 100 times this value in weights. Plus, every neuron also needs a bias term, which means that we have another 100 trainable parameters, which are the biases for the individual neurons. So, yeah, this is quite a lot, over 1 million parameters, just to extract 100 features, 100 patterns from our data. And this is just for a single layer. So now, if we were to build a model starting from this, now this is suddenly getting very unwieldy. It's a very, very big model. But maybe we can do better than this. Maybe there is a way in which we can actually have the same capability to extract many patterns or even more than 100 patterns from the image without having to actually have so many weights. And the way we do it is by designing a smart way to build our layers. And this is something that is very common in deep learning, which is let's try to see what are the characteristics of our dataset that we can exploit to simplify our neural network and to make it better for this task. So for example, in the case of images, if you think of an image of a cat, so there is, and you therefore want to have some neurons that extracts the pattern of a cat. A cat has a specific pattern, let's say a cat face, a specific combination of pixel values. But now if I put the cat in the top left corner of the image, or I put the cat in the bottom right corner of the image, this will still be an image of a cat. And the cat itself, in that corner, if you just look at the corner where the cat is, you will see the same combination of features, the same pattern that you would see if the cat was in the other place, just moved, shifted, translated into another location. And this is something that we call the translation invariance of images. And with different types of data, we can have other types of invariance. things that don't change when they get moved around or when they get transformed in some way. And we can exploit this. Then what we can say is that if we want to detect a cat, we don't need to look at all the pixels in the picture. We just look at a small part of the picture and see if there is a cat there. And then we can look at another small part of the picture and see if there is a cat there. And this is what we do with the convolutional neural networks, the types of neural networks that we typically use for images. So for example, whoops, now my screen has frozen a little bit.
No, yeah, no worries. We can still see the same document.
Yes, perfect. Okay, now I think it has unfrozen for me as well.
Oh, okay, excellent.
So let's try to build some convolutional neural networks, some convolutional kernel, as we call them ourselves, and see how they work. So I recommend going in this first link listed here in the lesson to see an example of this. So what a convolutional kernel or a convolutional filter is, it is effectively a neural network neuron that instead of looking at the whole image, only looks at a small portion of the image. So for example, in this case here, we have this image which is black and white. So we only have one value per pixel. And here we are building a filter that looks at a 3x3 box of the image and computes a value out of it. So for example, here we can see if I want to compute a value for the red pixel on the right, I can do that by looking at itself and the 8 pixels around it in a grid, as you can see on the left side of the image. And what we do in this kernel is we take the values of this neighborhood, of this area of pixels, of this chunk, and we combine them in some way to get the output. So the kernel that we have here is a very simple kernel. It takes the value of the central pixel as it is, with a multiplier of 1, and then it takes the pixels around it with a multiplier of 0, which means it's ignoring the values of the surrounding pixels and keeping the value of the central pixel, which means that this is just the identity transformation. The output is the same as the input. But we can use this approach to build some quite interesting transformations. So let's look, for example, at let me see if I can. My mouse is freezing a little bit. Sorry, guys.
No.
Let's
Yeah,
look at the outline. What it does is that it takes the central value and it multiplies it by 8. And then it takes the 8 pixels around it and multiplies them by -1. So what does this do? Well, you can see that 8 and you have 8 negative ones. So what is happening is that if you go into an area of the image where all the pixels are the same color or very similar colors, what you can see is that because there is very little difference between the middle and the sides, 8 times the middle minus each of the 8 sides gives you a value very close to 0. So we get a black pixel because values close to 0 are dark colors. And if we go in a place where all the pixels are, let's say, instead of very white, all the pixels are very black, like, let's say, somewhere here, we have the same situation. Now the pixel values are very different, but the same applies because the central value is very similar to the surrounding values. 8 times the center minus the 8 surrounding is a value close to 0. And this leads again to the output being black. But if, on the other hand, we go into an area of the image where some of the pixels have a very different colors than the other, So like, for example, here we have a pretty light value at the center, so a very high value in the center. So the center times 8 is a lot, but some of the surrounding values are lower, so they can't completely cancel it out. So we get a big value left out, which means that we get a very white pixel. And what effectively this does is that it gives us white where there is a change in color, in brightness, and it gives black where all the 8 pixels are very similar in color. So it has this effort, this effect of outlining the image, drawing the borders of the image. And with this approach, we can build a lot of different kernels. So we can build the kernels that do all sort of stuff. So we can build the kernels that blur images by basically just averaging out all the surrounding pixels, or values that instead try to sharpen the image. Whoops, that was not what I wanted. To sharpen the image by giving a higher score to the center than to the surrounding ones. So yeah, this is kind of the concept of these convolutional layers.
So how could ask perhaps one naive question, but like, so you showed all these kernels, and so how does it actually then work in a neural network? Can we expect that these kernels appear there, or like how would it actually be like here in comparison? Like would be the comparison in terms of kernels in a neural network?
Yes, that's very good. These are human-made kernels, were specifically crafted by a human with a specific idea in mind of achieving a specific effect. Handcrafted. But in a neural network, we do not handcraft this. We just have each of these kernels be a neuron. With the weights here are the weights will not be manually chosen by us, but will be trained during the training process, which means that we will not get kernels that have these clear effects that we as humans can easily understand. Instead, we will have these kernels that if we look at them, we're like, we don't know what this does. But the neural network internally is using those to extract some patterns that are useful for the neural network. And there has been research showing that these actually represent something often, like they can maybe extract specific directions of lines, like some try to extract horizontal lines, others trying to extract vertical lines. But it's never totally straightforward to understand what they do. Some of it is a little bit of a black box, and this is the nature of deep learning, where because we do not control the weights, we do not control what the operation does, the output of specific neurons within the network might not be understandable to us. However, it's still good to think in this way and to build this sort of understanding and intuition of what the model could be doing. The model is not doing this. The model found something better, some better kernels than what we as humans could build. But it's still using this approach of finding kernels that highlight useful patterns in the image. And that is the key.
Hmm. Yeah, I think that that makes a lot of sense. And I think this is also like something I think rightfully you emphasize that we are using deep learning, we give data, we define certain like architectures and loss functions and other things, but then basically we are mostly out of the loop to some extent. Meaning we can, yesterday it came also up this like approaches of explainable machine learning or AI. There's some like bridges we can build, but I think in general it is, and it's immediately quite obvious with these kernels here that there's something, some information that is useful, but we should really emphasize that useful is always the question should be for whom it's useful. It's not human useful, but machine useful. Yeah, exactly. Um,
Absolutely.
so perhaps another question now that you spoke so much about kernels here. So I think it will anyways come up very soon, but maybe would be worth mentioning here is so you have this here this 3 by 3 kernel. So what happens actually like at the borders and what is like how does it is it like somehow because you said the pixels get like kind of there's a sum and the multiply and so on, but I guess there's a problem when I'm at the corner or like at the edges there. So can you a bit explain what happens there?
Yes, and we can see it here with these question marks, right? I scrolled a little bit too much to the right, and now how do we work when we are missing some of the pixel because some of the area around the target pixel is outside of the image, and there are different approaches for that. So, for example, one way is to pad the image, just artificially add some extra pixels around it, which could be the same colors as the already existing pixels, or you could maybe add a black border around the image if you want. So these are different approaches that are used. Another approach is to simply ignore that and just say our output image will be missing the corners because we don't know how
Hmm.
to do that. So we are just having an image that is slightly narrower, in this case, maybe 1 pixel narrower in each direction. And that is also sometimes an acceptable way to do it. So
Hmm.
there are different choices and different models might use different approaches. They have limited effect on the final result. It's just different tweaks to solve this issue.
Yeah. So maybe to summarize in one sentence, this is a problem. There's different ways to solve it, but it's maybe not the most crucial problem we have, but perhaps it's something where like people who invent like or who create particular architectures make a choice and we maybe just accept this choice and then also maybe look at choices others have made to make our choice. If we, for example, get to create a new like own model.
Yeah, absolutely. So let us now move, or at least me move to our notebook, and I will be using the PyTorch version of the notebook for this, and I will be using my local data for it.
There was still like I think in the lesson there was one question that I find like interesting to ask. So it is about the number of model parameters, and I think it touches quite nicely on what we have been discussing so far. So I wonder if we should still like ask this question
Yeah,
from the
absolutely.
audience.
I was missing, I missed it, but yeah, we can absolutely ask you guys, what do you think if we now want to again have 100 patterns that we extract, like we did before with the standard neurons, we extracted 100 patterns. If we now extract 100 patterns, but we do that by using these 3 by 3 kernels, or in this case, 3 by 3 by 3, because while I showed you black and white images, we are actually using color images. So for every pixel, we actually have 3 values. So we have these 3 by 3 by 3 kernels for each neuron. So what will happen? How many parameters will our model have? And you don't have options here. You have to try to think about it. What do you think will be the correct answer?
Yeah, and I think it's also like fine to make somewhat informed guesses here, right? Like we're not like just go ahead and I guess it's like one thing that maybe one hint would be quite much less than with the fully connected dense network that we had before because that's the whole point, right? Like that we we kind of overcome this explosion here in terms of parameters. But yeah, the concrete number, yeah. We can wait slightly and then perhaps also like show the solution and how to calculate it. I just wanted to bring it up because I think it's like an important point here. Especially I think we so far have talked about very tiny images, right? Like 64 by 64. If you look at any like I have like some iPhone camera here or like some other phone, they make 4K images nowadays. So it's like it's very different, right? So it's a very important point to raise, I think.
So we have some answers that came in. So someone said 2,800, and someone said 3 by 3 by 3 times 100 makes 2,700. To which I answer, both these answers are correct. The question says, assume for simplicity that the kernels do not use bias terms, in which case it's 2,700. But it is indeed true that if you then consider that for every kernel, yeah, oh, that's cheating, changing the answer afterwards, guys. If you include also the bias term that in the real world we would actually have on every kernel, that lead us to 2,800 total parameters. So yes, correct, guys. And if you compare this with the million plus parameters we had before, this is a significant improvement. And these still give us 100 patterns. But instead of being 100 patterns that are collected over the whole picture, it's 100 patterns that are corrected sliding over each tiny patch of the picture. So I will
So,
now,
I
yeah,
just wanted to ask, like, just according to schedule, we should soon have some slight break so that people can digest. So I was just like wondering, like, just reminding you, like, I don't know when do you still want to do a little bit and then we do a break or
the plan is just that I now am catching up on the notebook.
right?
So I suggest let's quickly run through the initial part of the notebook if you haven't done already while I was talking. So we just load our libraries, we check our GPU or CPU device available, we load our data. For you, it's already set if you're on Lumi to the correct path. I had to change it because I'm running locally. So if you're running locally, change this to your local path. We've seen this already in the notebook, and we have seen our dataset in the notebook, which we now use to build our dataset class to build both a train and a test dataset or validation dataset. And I think we can now take a break. And when we come back, we will actually try to build a model in the way that we just described using these convolutional kernels. So
Mhm.
let's say we take a 10 minutes break and come back at 5 past 10. So I hope everyone is up to speed here in the notebook. If not, just if you have any issues, just write it down on HackMD and someone will try to help you. But let's, without further ado, try to build the model that a model based on this new layer that we just learned, this convolutional layer based on these kernels. So this is our model class. And one difference compared to yesterday is that we are using now this sequential approach, sequential style to defining models. If you remember yesterday, for example, we had layer definitions, and then in the forward step, we were calling them one by one. By using this sequential approach, we avoid having to do that. We define them here in the correct order with already the activation also set up. And then our forward statement becomes easier because the sequential class will take care of calling each layer one after the other. So this is just making our job slightly shorter when we need to tweak these models step by step. And what we're doing is that we're building a neural network where we start with two convolutional layers, and then we end with one linear layer to produce our classes. How this convolutional layer works is that we need to define, as always in PyTorch, inputs and outputs. So what we're saying here in the conv2d is that we are saying that our images have three input channels, as they are called, which means three colors, red, green, and blue, three components for every pixel. And we are saying that we want 50 neurons to operate on this. So 50 different kernels that will be iterating over the patches of the image and producing an output. So we will have 50 outputs. And what we are specifying is that each of these kernels, each of these neurons will observe a 3 by 3 patch of the image. So this is exactly what we did before with this 3 by 3 block, where this is defining the 3 by 3. But now we have not one value per pixel, but 3 values per pixel. So what this will do then is it will generate for every pixel by looking at the 3 by 3 pixels around it, it will produce 50 outputs per pixel. Which means that when later we apply another convolution, our input, instead of containing 3 values per pixel, red, green, and blue, it now contains 50 values per pixel, which are the 50 patterns around that particular pixel that were extracted by the first convolution. And again, we let these produce 50 new patterns, and again, we look at 3 by 3 areas of the image. Then we flatten this representation, and we apply a linear layer, which will take all the features that we have from the second convolutional layer and map them onto our 10 classes that we have, because remember, we are trying to do classification on 10 classes. And now before going further into what this does exactly, let's try to have a look at building this model and getting a summary for the shape of the layers in this model. So we pass that our input is an image 3 by 64 by 64. And we get a result like this, where we can see the shapes, the output shapes and number of parameters of each individual layer. And now I want to ask you a question. And the question is, what do you think? And it's quite a broad question. What do you think of these shapes and parameter counts? The linear layer has a lot more parameters. Why is that the case? And do you think that makes sense from an intuitive perspective? And the other question I want to ask you is, what the hell do you think is this flattened layer doing based on what you see here? So
is that an audience question or a Marlon question?
It's an audience question.
Okay, right.
We can give a moment
cool.
to the audience to think about it, and then maybe you can also jump in and say what you think about this.
Mm-hmm.
So I will try to copy this into our... So we gave a moment to think. Marlon, what is your opinion about this?
So maybe I start with the flatten. So they're like it looks to me, if I look at the output shape here, that before the kind of the layer before this where Federello is there, it has like I think 4 dimensions in total, like a tensor of 4 dimensions, and now it's then it's only 2. So I guess the first one is anyways always because it's one example. So so I would say that quite literally says or does what it says. It just kind of puts the whole like the multi-dimensional tensor into one dimension.
Yes, exactly. And this is really because the linear layer expects 1 dimension as input.
Mm-hmm.
But it also has, in a sense, this kind of at the very practical level, it's necessary for the linear layer to operate. But at a more abstract level, what we're doing is that we're saying before we were building images and we were building features for every pixel, right? So if we look at this convolutional, we have the image, which now the corners got cut, as we said before. So now the image is a 62 by 62. We lost some pixel, but now every pixel has 50 values. And then when we do another convolution, we lose again some corner pixels, and again we have a 50 representation per pixel. So we have per pixel representations. But now what we're saying is now we are taking this per pixel representation and we are saying now these are no longer per pixel representation, but now these are representations of the entire image. So now we are saying these are no longer local patterns. These are now patterns that apply globally at the image level that we want to consider, in a sense. We're moving from pixel patterns to image level patterns. That is logically what we are saying when we put this flattened layer.
I think a very, very brief maybe thing here, what I could ask you is, so how do I get these different like numbers there? So how I guess the first one is obvious, right? Like I have a certain pixels in my image, so that I would probably know. And probably the last dimension I would also know because I have 10 classes. So how would you approach getting these intermediate ones? So what is like, do you have some guidance there, perhaps?
Yes, so there is no obvious way to do this, but a typical approach in deep learning models is that you want your number of features to increase compared to the input. So typically you want, if you have, like in this case, it's trivial because we only have 3 input values per pixel, but you typically want to, in a bigger network, you want to slowly expand this number to bigger and bigger number of features per pixel to let the model extract more and more patterns. And then you want to go back and contract this number down to a smaller number towards the end so that you can select the most important ones for your specific high-level classification task. That would be my take on it. Here it's a very simple. We started with 3, we went to 50, and then we go back to 10 at the end. So it's relatively straightforward what is happening. But in a more complicated case, you might have 3, 50, 100, and then back to 50, and then back to 10. In a very
Yeah.
big model, you could do something to that extent.
I guess some of it is also sometimes trying something out and then getting some errors from PyTorch, right? That certain shapes don't match, and then you need to like rethink, like,
Yes.
oh, did I mess something up? So I think it's like you can calculate this before, but I think sometimes you still make mistakes, and then the framework will tell you what it expects. Meaning it says something like, oh, I have here so and so many dimensions, but you want me to have so and so many, so please, correct yourself, or there seems to be a problem.
Yeah. And that is important here for the linear layer, right? Because the linear
Mm-hmm.
layer has as many input features as the total output features over the whole image of the last convolution. So that's why this is 50 by 60 by 60. It's multiplying together the values from the last convolution. So we
Mm-hmm.
need to know that the image lost a few pixels along the way and that we had 50 kernels. But then the other point is the parameter count. And it's a little bit high for the linear layer at the end. Still, the linear layer is dominating the overall computational time, computational complexity, which is not that good because hopefully we want the convolutions to be extracting useful patterns. So here we are kind of diluting the power of the convolutions by having so many linear features in the linear layer at the end. So maybe this is something to be addressed to some extent. And the problem here is that, of course, the last linear layer needs to pick from the entire image, and the entire image is very big. But the way we can address this is by introducing a new type of layer into the mix, which is called the pooling layer. And what a pooling layer does is it shrinks the size of your image. It's in a sense, it's like you compressed your image. So you take, for example, a 4K image and you make it become an HD image, right? So you reduce by a factor of, let's say, 4 the number of pixels in the image while still keeping the whole image, right? You are not cutting parts of the image, but you're losing resolution. you no longer have every clear pixel that you had before, but now you have a little bit more blurry pixels. And this is what the pooling layer does. So I have here an image from a much bigger convolutional neural network. This is an actual network that was a state of the art a few years ago. And we can see how it operates. It takes a pretty big image. I mean, pretty big, much bigger than the one we are using today. It applies two convolutions on the image, going from 3 color channels to 64 features. And then it applies a pooling layer that shrinks it from 224 by 224 to 112 by 112. So now we have a smaller picture, much more blurry, let's say, intuitively. And then we apply more convolutions here. And then we make it even smaller. And then we apply more convolutions and make it even smaller until the image is so small, just a few pixels big, but with a lot of patterns in those few features, in those few pixels. And now this is what we actually flatten. So we first reduce the number of pixels, and then we flatten it into a single image level representation. And the powerful thing here is that because when you shrink the image, every pixel in the shrunk image is computed by taking 4 pixels in the original image. What is happening is that if you now do a convolution, a 3 by 3 convolution on this smaller image, it's like you are doing a 6 by 6 convolution on the original image. Actually, no, I'm completely wrong. It's a 9 by 9 convolution on the original. Okay, I can't get my math right, but
Yeah.
because every pixel is now 4 pixels, you are doing a much bigger, you're looking at a much bigger set of pixels from the original image, but you're not looking at them directly. You're looking at the condensed version of that through the pooling layer. And in particular, what we're doing here is a max pooling layer. So for every feature of the pixels, for every feature, we take the max among the 4 pixels that we are joining together. So the 2 here means we are taking a 2 by 2 square, and we are, for every feature of those 4 pixels, we take the maximum, and that will be the feature of the combined pixel.
Can I briefly
Yes.
interrupt you there? So if you go back to your like fancy architecture image you had there, so I think it's one thing we should emphasize here is so when you use this pooling, so this like red thing there, so can you explain maybe again, is this now like is it a part of the image or because I think this might be confusing to somebody who has never seen this before. Like how does it actually map?
Good point. So this might look like it's just the center of the image, but actually this corner here, the pixel that is here in the corner, is the group of 4 pixels that were here in this corner. And similarly, the pixel in this corner is coming from the group of 4 pixels that is here in this corner. So you can think of taking the big image, splitting it in 4 by 4 groups, merging those, and then shrinking them down and compacting them to be side by side with each other. So it's actually taking the whole image, not just part of it.
Yeah, I think this is important that we're not like doing any cutouts or anything, but we're just like pooling. Well, that's the name of the layer, but we are pooling the information into like a smaller matrix or smaller tensor, or you call it like a smaller image, but like somehow it's smaller. So I think that's very crucial to emphasize here. We are not losing any of the things. Yeah.
Yes, like someone wrote in chat, it's a coarsening. Yes, you are coarsening. That's another term that can be used. You are coarsening the image.
Mm-hmm.
So, and if we see the result of that, what is happening is that now we have these max pool layers, and when those happen, the size of the image gets cut in half in each dimension. So now we have smaller image going into the next convolution. This does not change the number of parameters of the convolution itself, because that is independent of image size. That is only a matter of field of kernel size and number of channels. But because the final image is much smaller, then our linear layer becomes much smaller than it was before. And this is important because now we are having a better balance and we have a lower chance of overfitting on this layer. And these features here will now be not specific to a very small part of the image, but they will be taken from a bigger portion of the image each. So they have a more give the linear layer a more global view of what is happening overall within the image. So let's now go and try to actually play with these models and train them. And I will not actually go too much into the details of the training loop, because it is actually very similar to what we had yesterday and the day before yesterday. We are still doing the same kind of things. We are building an optimizer in the loss function. We are building data loaders. And we are iterating for a number of epochs, doing a training and testing over these epochs. We are also storing all the information so that we can later plot it. And within each training step, we are simply taking each batch, computing the prediction, computing the loss, and in addition to the loss, we are also computing the accuracy, which is whether our prediction matches the ground truth. So epsilon here is our ground truth, is a number between 0 and 9. And what here argmax does is that it takes the 10 values, the 10 output neurons for the image, which is the probability of each class, and takes the highest number. So which class our neuron thinks is the correct one. So we just check in this way the accuracy. And we make these into reusable functions because we're going to train more than one model today. So let's now take our model, our latest model with the convolutions and pooling, and let's try to train it for a while. And this will now take slightly longer than how much it took in the last few days, because it's a slightly bigger model. And we are done. We have our model trained. Let's now have a look at the performance of this model. So we have this small helper that allows us to plot a specific metric over our training epochs. And let's look at our model accuracy. And well, what do we see here? Well, we can see that there is quite a significant difference between the training accuracy and the accuracy that we have on the test set. And this is not very good. On the test set, we are plateauing. On the training set, instead, we keep improving our accuracy. This indicates that our model is overfitting. We can also look at the loss function directly, and we can see that indeed, we are not improving on the validation set, but we are on the training set. So this is not the best model. However, it does reach a decent, at least best accuracy of around 30%. And one thing that we can quickly do is that we can try to compare this with what a dense model would do. So without using convolutions, if we were to train a model on this image in the naive way of just connecting neurons to every input feature. So we have 12,288 features. As we did before, we go into 50 patterns, then 50 into 50 again, and then 50 into 10. So in a sense, we are extracting the same amount of features that our convolutions were extracting before. And if we look at this model, we can see that it is actually quite big. It's bigger than the convolutional model we just had, simply because the linear layer that operates on the whole image is quite big. And what happens if we now train this? And hopefully the training on Lumi is also at least as fast as this, if not faster. Voila, we are there. So we can now plot this. And we can see that we are actually quite a bit worse than we were before. So before we were at, let's say, 30% max validation accuracy or test accuracy. Here instead we reach 22%. So the model is not performing so well. And this goes to show the power of the convolutional approach. Despite having more parameters, this model is actually performing worse. The reason being that we are not exploiting this characteristic of the data, right? Where we can actually reutilize the same filters to extract the same patterns in different areas. This is very powerful and helps the model train a lot better. But still, we are clearly not doing very well. Let's try to now take this step 9. Let's try to refine our model. And the way that we can refine this is by introducing a new approach, which is called dropout. And now I will go back here to explain to you what dropout is. Voila! So the problem that we are having is that our model is overfitting. On the train set, it's going better and better, but it's not improving on the validation set. This is showing that the model is memorizing specific training examples to become better at those. And this causes a loss of its capacity to generalize to new things that it hasn't seen, because it spent all its capacity really memorizing individual cases. And one way that we can try to address this is using dropout. What dropout does is that randomly, at each training step, we will remove some connections from the model. We will drop some weights or drop some neurons so that we are basically cutting part of our model. What this will do is that the model will no longer have access to certain patterns. So if before it was using a pattern horizontal lines, well, now this iteration, their pattern horizontal lines might not be available to it. It might have to do its prediction without knowing where are the horizontal lines, only using the information maybe of where the vertical lines are. But the next step, maybe, it will not know where we will cut out vertical lines at the next training step. So it will have to do the prediction knowing where the horizontal lines are, but not the vertical ones. And this will make it have to learn redundant information. So not only learn, okay, if I see specific horizontal lines and specific vertical lines, then it's this specific training sample. No, now it has to be able to generalize. Well, horizontal lines and vertical lines correlate in a certain way, and if I see one, I can kind of make a prediction without having seen the other. Or maybe, instead of always focusing on horizontal lines and vertical lines, when I don't know the horizontal lines, maybe I can use vertical lines plus semicircles to take the answer. So it forces the model to have more options and more redundancy in how it makes its predictions. And it makes it harder to memorize one specific example from the data. And this is a way to basically address this overfitting issue. So another way to think about it is that you can recognize an elephant even if you can't see the color. If I draw the outline of an elephant but don't color it in, you can still tell it's an elephant. You don't need all the information to decide that. And if I gave you all the information, maybe you would overfit and know exactly which elephant I'm talking about, which is too much. It's not maybe what we want to do. I don't know, Marlon, if you have some comments on this, because it's quite an interesting approach.
I think this is quite interesting. I think there's maybe two questions that come up for me. So one is you spoke about this dropout. So what does actually happen if I use the model? Like so I train it but when I use it, what happens to the dropout actually?
Yes, when we actually use the model, we don't do the dropout. The dropout is only during training. We are giving the model a very hard training, but we are not challenging the model during inference. In a sense,
Hmm.
if I wanted to be able to run a 5 kilometer without breaking a sweat, I will train myself to run 10 kilometers. And then running 5 kilometers will be easy for me. And that's the same thing here. We train the model to do very hard predictions where much of the
Mhm.
data is missing. And then the model will be able to do prediction relatively easily once it has all the information available at the same time, even if maybe the input data will be a little bit noisy. But we
Mhm.
already made it very noisy during training, so we kind of addressed part of this.
And then yeah, I think this makes a lot of sense, right? Like you want to train, yeah, as you said, train hard and then test maybe not so hard or perform better. Um, so then another obvious choice or like obvious maybe question here is, okay, so how much do I drop out and how do I choose like the parameter? So you had there, if you go back to your code, there was like some number there. So I guess that means like 50% get drop out. So I mean I could might as well take, I don't know, 90. I might as well take 10%. So can you give some guidance on that perhaps?
Yes, so this is something that is very hard to pick by hand. So depending on what kind of model you're working with, there might be some good standard practice for this. But it's something that really needs experimentation to find out the best value. And we will get to this experimentation very soon on how to do that. But
Mm-hmm.
I would recommend maybe starting, yeah, around 50, maybe 60% would be my personal recommendation in most cases. But you can actually be quite aggressive and drop out a lot of the data. And we can see that these dropout layers, they don't affect the model parameters at all. They will simply cancel some of them out dynamically during training. So let's now try to train this particular model and see what happens. And in the meantime, while this model trains, let's go back to the question that Marlon had about how do we select the best dropout value. So here we are dropping out 50% every time. How do we know that this is good? Well, we don't really know. We need to find out. And the way we do that is by using an approach that is called hyperparameter tuning. So hyperparameters are things, configuration values that you need to pick when you build a model or when you train a model. It could be, for example, how many convolutional layers should I have? How much dropout should I have in my model? Or what should be, how many epochs should I train it for? Or what optimizer and loss function should I use? These are model hyperparameters. And it's very hard to answer these questions in general. It depends a lot on what model you are building. So what we often do is we don't just pick some values, but instead we actually try out different combinations of values. So let's see how we do that. The way we do that is that instead of building a fixed model, what we do is that we build a configurable model. So this model here, where we need to pass in a dropout rate and a number of layers. And what this will do, oops, if this works, arg. Okay, what this does is that it creates a set of input layers. So we just do a first convolution, ReLU, and a first max pooling. And then after that, it creates a dynamically sized number of hidden layers, all of the same size, 50 convolutions, all followed by ReLU and max pooling. And the number of these will be based on the number of layers that we pass as input. So we can dynamically choose how many layers we will have. Okay, it's again freezing for me, unfortunately.
Yeah,
Um,
but basically what you're describing here is like the, I guess what people have been asking in the last couple of days a lot, right? Like
yes, exactly.
so this seems all like a little bit like black magic. So how do I actually pick the things? So I think this is exactly this um this aspect here. Like how do I pick dropout? How do I pick the layers? How do I pick stuff like learning rate? All of this. So I guess it's like I just briefly emphasized this here. So this is usually something where picking by hand reaches its limits, but now we go to more kind of automated approaches, and because well, as we emphasized before, we as humans can hardly like imagine sometimes what is a good choice and what is a bad choice. So here then we go in the direction of automatically picking that. Yeah.
Yes, very, very good point. And by the way, there is a question in HackMD. How do we compute the size of the dense layer after flatten? Well, here is the formula. If you know how many convolution layers you have, you can actually, and how many pooling layers you have, you can actually compute how many features you will have at the end. Because every convolution removes 2 pixels in this case, because it's cutting the corners, and every pooling layer cuts the number of pixels by 2. So here, because
Mm.
we don't know a priori the number of layers, we have to dynamically compute how big our linear layer after flatten will be.
Yeah. So maybe two remarks. So first, in terms of schedule, I know that we are like a little bit over time in terms of what we allocated, but the last session is maybe a little bit briefer than what is allocated. So we're in general fine. So I think we will continue with this and then take a break after. So don't be afraid you don't get a break. You will get a break. And then the other thing, there's two questions in HackMD specific to dropout. So one is basically the decision what gets dropped out. Is it for one epoch? Is it for one batch? Or that would be maybe something we could briefly answer.
Yes. So this is for every training step. So if we go back to the training loop, which I kind of glossed over, every time we get a batch of data, so every step, every batch within an epoch, when we call the model, this is the point where the dropout gets chosen. This is the point where it gets chosen what to drop out. So for every batch, it's going to be different. And because batches are randomly shuffled, this means that at the next epoch, the same image as the previous epoch will be dropped, will have different things dropped. And what gets dropped out is entire filters, because the dropout is applied afterwards. La, 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 la. I will now try to find out. Yes, so it's after the max pooling, which means that after we have these pooled pixels, what happens is that some features of these pixels will be dropped out. So, and effectively, because these features come from the filters of the previous convolutions, it's effectively entire filters of the previous convolutions that gets dropped out.
Yeah. I think that answers at least the questions that were flagged for us in the HackMD. I guess don't hesitate to ask them more questions, but maybe we can proceed for now.
Yes. So I can actually answer already a question from there, which is what we are tuning in this specific case. We are trying now to tuning the dropout rate of the dropout layer that is before the flatten, and how many convolutional plus pooling layers we have in the middle of our architecture. And what we do here is that we will do what we call a grid search, which means we decide what are acceptable combinations and we test all of them. So for example, we decide that the hidden layers should be either 1 or 2. We think these are good values. Maybe we want 1, maybe we want 2. We don't know which one is better. And for how much to drop out, we think somewhere between 20% and 80%. And let's say that we want to try 3 values in between here. So this will actually say, this command will actually create a list which has 0.2, 0.5, and 0.8, because it's 3 values between 0.2 and 0.8, equally spaced. So we have now 3 options for dropout, 2 options for how many layers. Let's try all of them. Let's try one layer 20%, one layer 50%, one layer 80%, two layers 20%, and so on. And we do that in a loop. We loop on every potential combination, and for every potential combination, we actually train a model. And then we look at which model got overall the best training loss. And we save that model. Which model, we keep track of which model is the best model we've seen so far. So let's start
So
with, yeah.
Yeah, I just wanted to say another illustration is you can think of it as a chessboard, right? So you have this grid and then you try out every part here because it's a 2D thing. Um, maybe one thing to ask here, is this really like, is this the thing people do, or are there like other ways of doing this? So are you always thinking in chessboards or like higher dimensional like tensors of trying every grid cell, or what could be other things, or should kind of what would people use usually?
That is a very good question. And the answer is we can't do this. This is not scalable in practice because you might want to try a lot more number of layers. And then you might also want to change the size of each layer and the dropout rate, and then maybe the size of the kernels, and then so the number of channels. So there are so many, and then maybe every layer could have a different number of channels, actually. They don't have to all have the same. So the number of combination to test is huge. You can't possibly test all of them. So there are algorithms, there are methods that help you do this. There are methods to define this big space of all possible combination, but then instead of trying all of them, strategically try a few of them and make an informed decision based on the ones I tried so far. What should I try next? What is most likely to give me good results? So there are algorithms for this, and there are libraries that implement these algorithms. So now we are looking at this by hand because it's important to understand how this works internally. But in reality, you should never do these for loops by yourselves. There are libraries for both Keras and for PyTorch that can help you do this automatically in a more efficient way while you spend your time taking care of other things while this runs in the background, doing all the model selection.
Hmm.
By the way, while this is training, oh, this is done training actually. We never checked, that's perfect time, but we never checked our dropout model. And what I want to show is that adding the dropout actually did improve our model. Now the validation, the test accuracy, and actually this is the loss, but the accuracy is the same. It's now tracking much more closely with the training one. So our model is no longer overfitting.
Hmm.
And if we look at the result of our fine-tuning work, we can actually ask, which is now our best model? And what this found is that the best model has two layers and a 50% dropout rate, which is exactly actually the model we were using before, which is why we're using that. And it tried 6 different models, all the different combinations. And now that we have the best model, we can now save it. And voila, we can reuse it in the future to predict things. And this leads us to the end of this part, which I am very sorry went slightly over time. And maybe one point to take into the break could be the fact that these models, yeah, we build some nice models that do things, but even our overfitting model in the training set was having like 45% accuracy, and in the validation was doing 30%. The one we drop out is not overfitting anymore, but it's actually performing at 20% validation accuracy. These models are not very good. We are not managing to get good results out of this. Building our own model and training it on the dataset from scratch is actually not giving us decent performance. So the question is, what can we do? Now, this didn't work out for us. What are the alternatives? And I think Marlon will get into that after the break.
Yes, exactly. So after the break, we will look at this paradigm of training called transfer learning. So perhaps we could, maybe it's easiest we just continue at like, oh no, I need to. So it's 11 then, right? Like I'm in Finnish time zone. So like, well, in like 10 minutes
Yeah,
roughly.
like that means it will be 11 in European time.
Yes. So then we could continue and then we look at transfer learning, and I think that's also like a very interesting aspect. Yeah. All
Perfect.
right,
See you
then
later.
yeah, see you in a bit. There are certain like other languages that are, let's say, a bit more specific. So I think there's also like something really to bring up here, that this seems like a nice thing to do, and it's very useful for many things, but it's not easy to get started and identify. Um, yeah, so this is kind of the thing we will look at here, and as I said, we will first. So the data here is the same as before. So we are not changing that, and we are not like kind of, well, we have looked quite extensively at this data, so it's still 64 by 64 images and three color channels, um, and we will now like move on there. So this is not the interesting bit here, but what is maybe interesting now is that okay, we we had this previously, like Ludovico introduced this data set class here, this custom one, and he already teased to you that okay, what happens if you want to do specific modifications to it? So in this case, what we do is that we have here the same, very same class, should be very similar to what we've seen, but we have a new parameter here, attribute we can pass, and it can be a function. And what this does is that when we get the item, so when it's used, then if this is defined, this function gets applied to the data. So this is something where now we can do different things to the images, and it gives us quite some powerful kind of, it's easy to express a lot of transformations here. So meaning, so not only this stuff that we anyways have here, like for example this normalization or this permutation that we talked about, but now we can do basically apply any function that we would like to this. And this is usually what you have in this. Also, when there's like a pre-made data set, that you have the ability to pass a function. And now you might ask yourself, like, okay, why is that? So I'm for now going to continue in this, but soon when we go actually to the training, we're um, gonna swap to the Jupyter notebook again. But now, when we start using a pre-trained model, um, it's not necessarily the case always that every pre-trained model fits our data immediately. Meaning, our data here has 64 by 64 pixels, but of course, that's a very unique like maybe not unique, there's probably others that have this, but it's not, you cannot take it for granted that every pre-trained model, every existing model in the world that you might want to use has exactly this 64 by 64 pixels. But it could be that there's, for example, more pixels here, so it's kind of trained on bigger images. And what we do here is, so this is of course something that you would do in practice a little bit like iteratively. So you wouldn't like start and knowing, okay, I need to adapt my data to a certain size, but first we would probably pick a model. So it's now here, logical flow is maybe not optimal, but we are now going to assume before actually looking at the model that we are going to train, um, that we're going to assume that this model doesn't take 64 by 64 pixels, but um, quite much larger images here. And what we are going to do is that we are going to define a function here that is basically what it's doing is taking our image and then making it larger. So there's very different ways of doing that. And there's very specific things. So you can see, for example, the Keras version of this does it slightly different in the PyTorch. But generally, the idea here is that we have our images, they are of particular size, and we kind of enhance or increase the size here. And then when we actually create our training and validation data sets, we are passing this function. Um, so this is really just taking our images and now we can adapt them. And the powerful thing here is that when our model changes or when something changes, for example, now with the next model, we don't want 160 pixels, but we want, I don't know, 224 by 224 or something else. Then, well, we really just need to adapt this function. So because we previously made this attribute to the data loader, to the data set, now it gives us the flexibility to adapt. Um, yeah, so I wonder, Ludovico, so far, is there anything you think I missed, or should we move on to the actual model?
I think this is quite clear. Now the question is, let's when we move to the model, like where do we get a model to use?
Right. So that's a good question. So in this particular like exercise here, we are not really like giving you the challenge of finding a model, but instead we are giving you one. So this one is a so-called DanceNet 121 or 121. So this is not like you don't need to understand the details here, but it's basically um, a model somebody has created. So there's a research paper on this. It's quite old for deep learning, but it doesn't matter. It's like from 2017, and this model has been uploaded to a repository. So you can think of it that in the internet there's many pages or many different libraries. So also kind of specific Python packages that allow you to instantly kind of download the model into your framework, so into PyTorch and Keras. And you just need to, so your challenge is to identify which model do you want to use. And then it's quite easy to actually use it. Um, so we so I'm not sure if that answers your question. It's a bit abstract, of course, but you can think of it as there are places to find these models, and then we, for example, use this torch vision models here, and I think in Keras it's Keras applications, but there is, for example, also there's this Hugging Face that was mentioned yesterday, Hugging Face Hub. That's another big repository. Um, I think, um, yeah, there's just like a lot of stuff out there, and it's good. You can find it, and I guess we can also point you to some of these. But here, we already uh, said that okay, well, this model it has seen data already. So here, this model has been pre-trained on the so-called ImageNet datasets, which is like a very common dataset. So basically, you can think of it. It has already learned to classify, in this case, 20,000. So a lot of different classes, um, based on over 14 million images. So if you think of this as a computational problem, this took a lot of compute already. And what the idea is here, you don't do this yourself, but like somebody has done this, and you can build on top of this. And we will okay, here it says we look at the architecture. I wouldn't like now start looking maybe at the architecture too much. I would just take this as an example So there are certain models out there that are very big that you can use. Mm, yeah, so what we could do now, so I read at least that now maybe the file system problems have been solved. So we could move to actually using the model.
Yeah, I can confirm the problems have been solved, so it should be
Okay,
possible to load and
right.
store information on Lumi.
Okay, well let's go and let's try. So I'm gonna just do these basic steps here that we've been doing the last sessions also, and I'm gonna go all the way that, okay, this I have explained, right? This transformation function that gets passed here. So now, and this is always slightly different in Keras, in the PyTorch, and if you use other framework, it's a little bit different as well. But what we do now is that we create a model. So this is very similar kind of thing that we've done so far. But instead of using more, like certain layers, we use in place here basically the existing model. So here, what this means is that we use this from torch vision models, this dense net. Weights here means, okay, this has been pre-trained on ImageNet. And now the tricky part here is that we don't want to use the whole model, but we just want to use the part at the beginning, or well, essentially it's most of the part, but up until the part where we actually start going to classify. Because of course this changes now, right? So this has been trained on 20,000 different classes, and now we have only 10. So it's quite obvious that we only want, so this basically this dot features here, and in Keras it's slightly different, just means we take a part of this big model. And then what we do is that we build a classification layer on top. How to do this in practice? I think there's very different like ideas of how to design these classification layers, but you can just take it as kind of given here that, well, a huge part of the model has been already trained, and we just use it as it is, and then we build something on top here, so you can recognize certain layers as before here, and then in the forward pass. What happens is that so first we apply this pre-trained model to the image, and then in the end we flatten it. So that's what Ludovico has been talking about, and then we get a vector here of size of dimensionality of 1024. So you can think of it. We use this pre-trained model to map our images, do all the feature things, and in the end, we just get one vector out of it. So we we kind of use this just as some people call it even feature extractor. So we extract the just the features here. We don't care like how these have been produced, but we just they are useful, so we just use them here. And then for our actual task at hand, we kind of only classify, we only do our classification based on this one vector here. One thing to keep in mind here, when you start downloading these pre-trained models, they are somewhat large. So here I hope this doesn't screw us now, but I by default this goes to your home directory, and that's not a sensible place to save these models, especially on Lumi, because then your home directory will be full quite soon, and you will find these after months, and you're like, okay, why is my home directory full? Oh, I have all the old models there. So here, what I do is I save it to the current working directory because I'm on Scratch, so I know there's space. I hope now that the people that use project on Lumi, that this is not a problem for them. Um, but yeah, so now we have defined our model, and now what we do is I just quickly execute it, and then we can discuss. But basically, this now downloads the checkpoint. So basically, the pre-trained model is now downloaded. For me, it doesn't say anything because I already downloaded that.
Marlon, if I can stop
Yeah.
you before you go talk about this part,
Yes,
and
sure.
ask maybe a couple of questions about the model class.
Mm-hmm.
So one is a little bit, so one, let's say, smaller question is the 1024. So
Mm-hmm.
that is coming from the architecture of this dense net, right?
Mm-hmm.
So effectively, we know that this dense net will produce, the features part of the dense net will produce 1024 dimensions. So that's
Yeah.
why we use that as the starting point for our head.
Yeah. And it's like some of these are, so for example, certain, if you go to other architecture, certain vision transformers of certain size, they have certain dimensionality. It's just something that is defined. And some of the stuff that is built on top here, I wouldn't pay too much attention to that. But basically, yeah, you get this vector. So your image gets transformed to this vector and it's a fixed size. It's not your choice. Somebody has made this choice for you.
Yeah, so the model creators. So yeah.
Yeah, exactly.
And then my other question is maybe not really a question, but a comment on demystifying a little bit these dot features,
Mm-hmm.
where this DenseNet is just a model class similar to our model class. And in our model class, we define this as self-backbone and self-head. So then we can do model.backbone and model.head to get the two parts of the model separately. And this
Yes.
is the same with this DenseNet. This DenseNet internally has a self.features and a self.classifier or something like that. And we just want the first part. So we just do dot features and we get let's say we get the sequential part that contains all these conv and max pool and relu one after the other, but without the part of the flatten because that is in a different part. The same as for us, that we have two sequentials, one for the backbone
Mm.
and one for the head. So similarly, it's what is happening inside DenseNet, and this is what allows us to pick only the first part.
Yeah, exactly. That's thanks for raising that. Exactly. So we are just we know that there's this subs so you would know and then you would now pick it only. And now what we do here, I think I already hinted this a bit. So now this is also similar in Keras. So we create a model and now we say that okay, we don't want to adapt the whole model, right? Because we believe that the people who have created this model, trained it on a lot of data, have ensured that um, that these features that come out, so this feature vector, that it's sensible. And we don't want to mess with that. And especially we don't want to mess with it because it's a very big model, right? So it is computationally quite costly. So instead, what we do here is that we, in PyTorch, you can do this params requires grad false. So basically for all of the backbone parameters, so all of these, we just say, okay, we don't touch them. They don't get adapted. So what does this in turn mean? Only the classification head gets adapted. So this works very well if our kind of the data that the model has seen before and the data now are close to each other. But when the kind of the data and so kind of the data that has been seen before and our data is further apart, then we might want to do other things. I don't know, Ludovico, do you want to briefly like mention some of these, like other approaches perhaps, or
Yeah, I was thinking maybe we can go through that later, but yeah, this is not the only way to do things, right? You
yeah,
can you can basically decide to only train the top, but you can also decide to train everything, but maybe train it only a little bit. So, and that is kind of like saying you are still training a model, but instead of starting from scratch, starting from a random model, you are starting from already a decent guess. You start from a reasonable first approximation of the solution so that you only need to do a small change to the weights to get a good model. While normally when you build it from scratch, you start from random. You start from a model that makes absolutely no sense in terms of parameters. So there is a lot more work to do there. So
Mm-hmm.
it is possible to do it in this way. There are also some very advanced techniques where you can actually very efficiently modify some layers without training all of their weights. So you have some very big layers with a lot of parameters, but you can actually modify them by training only a few parameters. So there are techniques for this. The most famous is called the low rank adaptation. We will not go through it here, but there are approaches that make this transfer learning, or this sometimes we say fine tuning of model, make it a lot more accessible to limited compute power.
Mm-hmm. Exactly. So basically I'm have here like a laptop and if I just like would want to fine tune or like train the whole network, that would be like possibly not possible, but like just as lastly I could actually run on my laptop. So but then of course if you have Lumi at your access and you really need to do it then um well then you can do more stuff, right? Okay, I think we come to the first part of the exercise, if I'm not fully mistaken. So now we could print this summary here. Let's see if I can do it. Yes. So we use this summary thing here, and we say we don't want to see all the layers because there are so many. So we reduce a bit the um, depth of this so that we can actually print it. And there are two or three questions in the that we could answer here. Um, so I'm gonna just post them here. Um, so basically the idea is that so I posted them to the HackMD that like so first question is how many parameters are there and how many of them are trainable? Okay, why is this? And then can you see in the model what is the part of the base network or we call it backbone and what is the head? And then this is something very specific to Keras, so there's some stuff being passed there. I think the people with PyTorch can ignore that for now. And so basically, in for these answers, maybe one thing to mention here, the number of parameters are slightly different for Keras and for PyTorch. So don't worry about that. In the ballpark, they are like the same. So maybe we could give some time, and then maybe we can Ludovico can be the person answering these.
Yes. So we are starting to get some answers for the number of parameters.
Mm-hmm.
And indeed, Torch info makes it relatively easy for us. The total number of parameters is slightly over 7 millions. And however, most of those we can see are in this first sequential, this sequential 2-1, which if we go look at the class, is actually where we have our backbone, where we are taking from DenseNet. So it's actually this DenseNet dot features that is this sequential 2-1. And those we set requires grad to false. So those are not trainable. So in the end, the only trainable parameters are the one in sequential 1-2 in our new head network, and those are 53,000. And now,
Yeah.
how does this affect the time it takes to train the model? Well, it's relatively easy to imagine that the fewer models, the fewer parameters you need to train, the faster the process of training the model will become, because it's a lot fewer operations that are being performed. The backpropagation part is going to be much faster. The optimizer step will be much faster.
Mm-hmm. Exactly. So this is the powerful thing, right? So if you compare to the previous models we've been seeing, I don't think we have been coming close to this number ever. But then we will see very soon that actually using this model is not like it doesn't take forever. Like because the actual like trainable parameters are way smaller. Of course, there's some cost of kind of using the first part of the model, but it's like in comparison to actually adapting the weights, it's way smaller. Um, yeah, so I think you already touched this like head and base or backbone. I think this is in Torch maybe not so easy to see, but I guess based on the class we can identify like that this is the backbone and this is the head here. But yeah, and you can see here these are in brackets, so that I guess means in this case that they are not trainable. Um, so yes, so basically we have now at our hands a very powerful model. Um, of course, there's like way bigger models out there. So this is just one example we took. And we could now, so we are now using basically the very similar train and tests from earlier, and we could just start training this, and it might take a while, but we are now doing nothing really different. So basically all the steps are still there. All the building blocks you've learned over the last days are still there, but the thing is that we just swapped the model. So basically we still have this train and test. We still have this history that we have used earlier. We have training and validation loader. We have optimizer, loss function. And then I think this early stopping, if I'm not wrong, that was also, I think, briefly introduced yesterday, if I'm not mistaken. So maybe as a reminder, what this is that so this part here is like, okay, when we just for now say we train certain a number of epochs, I think it's 30 here, and then we say, okay, if there's no benefit in like continuing to train anymore because our validation loss doesn't improve anymore, after a couple of steps or epochs, we then stop the training. So this kind of prevents us from basically from wasting compute on or wasting our time on something that seems to be not getting better. So sure we are on Lumi, but still like it's just a GPU, so it's not like it's not so if you look at the time, I think compared to yesterday, it actually didn't take so long time. And then we can now could plot the results. And we see many interesting things here. So first of all, we see that okay, so there you see that the training accuracy went up quite high actually, and the validation accuracy also went up, not as high. So there's a gap here, but still we are like looking at in the end something like almost 70% of accuracy. And then what we also see is that actually this accuracy it shoots up, right? So it's like we see here that um, because we have a good start, right? It doesn't take us long to get to a reasonable. So even if we would now say, okay, we stop at like 4 epochs, so much less epochs than before, we would already get like somewhat good model. And the reason is just that somebody else has kind of used a lot of computational power before to adapt this. So it's like this warm start, or what Lodovico said. Also, even it's just not random weights, but it's has already seen some stuff. So it's very powerful and also reasonably fast. But of course, the catch here is always it needs to match, right? So basically, you need to find a pre-trained model that fits to your like that is somehow reasonable starting point here. Yeah. So
And
so this
maybe,
is yeah, sure.
yeah, maybe like here it's in a sense we haven't gone into it, but the ImageNet dataset is a
Hmm.
dataset that this model has been trained on initially. It has a broad variety of images in very different contexts. And we are now
Hmm.
also passing a broad variety of images in very different contexts. We from
Hmm.
shoes to lamps and so on. What do you think would happen, Marlon, if our task that we wanted to do was distinguish specific species of parrots from one another. And we had a
Um,
small data set for this, and we started from this model trained on ImageNet.
yeah, so I think once we which categories of things? Sorry, I didn't catch that.
Let's say parrots.
Oh, yeah, yeah, okay,
Anything,
parrots.
anything very specific.
Yes, yes, exactly. So I think so to some extent you would probably be able to do something, right? Because the lower levels, like it's able to the lower like with lower levels, I mean like early in the network, it's able to recognize certain shapes and all the things we discussed. But I guess to some extent it could be, if it's a very specific problem, it could be that maybe some of the, maybe for certain like very like parrots or what, or even like some medical images or whatever, then it might be that there are certain features now missing, right? So it has maybe useful features, but maybe for certain things, maybe it becomes it's a very like particular thing you need to distinguish. So I guess then we could get into troubles of okay, maybe we cannot use the backbone as it is, but we need to adapt it. Um, because maybe certain shapes are just maybe they are irrelevant even. Maybe certain features are just irrelevant, right? Like if you naively think of this cat and dog example I had in the beginning, and then you go to, I don't know, to certain birds or whatever, maybe, for example, whiskers or like paws, they are not like really relevant anymore. Of course, we think of this is a humanized like interpretation of the thing, but still, it's like makes a lot of sense to say that, oh, yeah, so certain things might not make sense, and then you need to adapt, and then you go into a very like I think rich field of how to adapt. So you mentioned you could adapt the whole network, but you can also do like maybe computationally like a little bit smarter things. Yeah, but it's a good question. Yeah. So, I wonder, like, so what would you suggest if people want to use this? How should they get started? Do you have some like if they have certain problem, like let's say I don't now want to do the problem you mentioned. So where should I start? Is that maybe like a useful discussion to have here?
Yeah, I would say you should start by looking at what similar data sets and what similar data sets there are online and what models there are that have been trained on these similar data sets or what
Mm-hmm.
models there are that have been used for similar tasks. So basically,
Yeah.
it's scouting what is available that is similar to what you need. And that is
Mm-hmm.
the starting point. And when you find something that is similar, then you maybe need to check how similar it is and start playing around and seeing what happens if I simply swap out the head. How does it perform? Well, what happens if maybe I adapt a few more layers? I let a few more layers be modified with some maybe of these advanced fine-tuning techniques that we didn't check today, like LoRa. What happens if I attempt to do those? Does that improve performance? And maybe
Mm-hmm.
try out, do some hyperparameter tuning in effect, trying out different things. And
Yeah.
but really starting from what is similar out there. That is the key point.
Yeah, yeah, I can only like underline that. That's a very like reasonable thing to do. And then I think maybe one thing we should also mention, because we now tell people to go out and download models. So of course, like whenever you download something, you need to know like you should trust the source, right? So even on like very established pages like Hugging Face or like this Vision, Torch Vision or so on, you need to like of course always like you should really check what you're doing because you are essentially downloading something to your machine. So even there are certain guardrails in place, I believe, but still like it's important to know that okay, now you're downloading something to your system, so it can be potentially not nice. And then also, I guess you don't really know what have they been training on. I think this is also something we discussed like earlier today we discussed, oh, the internet is big and people use all kind of data, but you don't know, right? So it could be that there are certain images being used, or especially if you go to like out of the image domain, you go to language models, right? And then suddenly this language model says something quite offensive, right? And you're like wondering why. Well, maybe you have adapted it from something that has seen something it shouldn't have seen, right? And I think this is
Yeah.
something that's maybe important to mention here.
Yeah, and anyone can make any models available online. So I can take a perfectly fine model and I can say, hey, I uploaded my own version, which has been tuned on some data. And when I do that, I might actually on purpose tune it in a way that it will produce wrong answers. It will produce correct answers most of the time, but wrong answers in specific cases. And this could lead to some pretty interesting exploits, where actually I can actually break some systems by tricking people into using a model that I specifically built to do the wrong thing, but not always, because otherwise people will realize, but only do wrong thing in specific circumstances. That is very evil and is something to pay a lot of attention to.
Mm-hmm. Exactly. So maybe one thing, and I have to confess, I don't really particularly know the answer to that. There was a question about this adaptive max pool, why we should use it with certain parameters. I have to say that I haven't looked into that too much.
I can give my opinion into this.
Yes.
And I will admit that I haven't looked into the exact shape of the model we are using. But what adaptive pooling does is that it basically takes an image of whatever size and does max pooling to the size that you want. So by passing 1, 1, we are saying whatever you get, make max pool all the pixels together. And this can be useful if we can't be bothered checking what is the size of the output from the previous layer. Then if you're like, I'm not 100% sure, I don't want to do the math, I just want to make it become 1 pixel. And this adaptive max pool will do that. One place where it can be very useful is if you have images of different sizes. If your input images are different sizes, the convolution will not care. It will just produce output images of different sizes. But when you want to flatten, then it will become a problem because flatten does care about the size. So this will basically say, go from variable size to a specific size. In our case, we know that all images have the same size. So here is just a fail-safe to make sure that whatever we get from the pre-trained network will be a single overall representation that we can flatten.
Mm-hmm.
That's effectively
Yeah.
what we are doing.
Yeah, that makes a lot of sense, and thanks for answering that. I think one th last thing we could briefly talk about because we mentioned it. So we talked about this pre-trained model libraries. So just to give one example here, there's like from this Torch Vision here, then you can see here there's quite some layers here, right? It's quite some models, and then you can see how do they perform on certain image net data set. And you can think of that all these kind of similar kind of repositories of models look like that. So they have for certain kind of tasks, they have then kind of pre-made models. So here's, for example, object detection. They have then like other models for video classification and so on. And this is just one example. There's many out there, I believe, especially like Hugging Face has like way more of these. But just to give you an example, where you would go, so then you can basically like load them, and then you see here, for example, there's sometimes also different versions of the weights. So, for example, this one gives like less accuracy than this one, and because maybe somebody has improved the pre-training of these models. So I just wanted to briefly show this. Um, that you have some idea that it's not too abstract. So there's repositories people can upload, as Ludovico said, anybody can upload, so that's a bit dangerous maybe, but you can also usually follow like um, how often has it been downloaded, and is the person uploading it, is it some reputable like person, or is it some random username you have never heard of before? Um, I don't know. Final, should we look at, is there anything still we want to mention on transfer learning? I don't know. Or should we maybe give over to Ashwin and do the closing?
I think we can go to the closing. I had a look at the HackMD and I think we covered
Okay,
all the main
great.
points. So
Great,
yeah,
great.
I think this is the end of this part, and then Ashwin can take over.
All right.
Ashwin, do you want to share your screen or?
I can share the screen. Yeah, thank you.
Okay,
Can do that.
thanks a lot.
Yeah. I think it was a perfect ending, how you wrapped up to be optimistic, but at the same time cautious. So it's a very good point. And that's also part of the message that how we are going to end this also. So the question maybe we are trying to answer at this stage is like, where do we go from here? We have learned a couple of architectures in this course, couple of different tasks, things to improve your training, but how does it apply to your particular problem, a real world problem that you have in mind, and what is the next step? Uh, so just to show like how similar a real world application will be look like, we can quickly take a look. We don't go into so much detail, but we can quickly take a look at a research which was already published, and they had done it in an open science approach. So they had even shared their notebooks, so we can look at both. This particular application has something is coming from the field of chem informatics. What they are trying to do is trying to see how similar two chemical molecules are based on their chemical properties. And in particular, the input that they are providing is mass spectrum. So mass spectrography. And I must admit, I just have a high school knowledge of chemistry. I turned into physics afterwards, but still I was able to understand uh, what they were going through. So if we click on this notebook, sorry, yeah, we'll look at the paper first. So what they're trying to do is trying to ingest two kinds of inputs and not one like we were doing. So the network looks very different, but at the same time you find some similarities. This is spectrum can be interpreted as a 1D image of a 1D vector with some sort of signals. What they're trying to look at two different spectrum, transform it into a higher dimensional space. Look how similar they are using cosine similarity by taking a dot product and see how apart they are in this higher dimensional space. But if you look at the workflow itself that they have in the notebook, it looks roughly the same thing that we are doing. So they import a couple of libraries. They use Keras here, and they have their own workflow for ingesting the data. So it seems like they have done a lot of work, like we were discussing, to clean up the data, to transform it. They have a specified way of loading it. They use their own pre-processing workflow, transforming their data into a form that the machine learning model can understand. And if we skip to the model training part, it starts to look very similar. They choose a model architecture that they created. They have an optimizer. They specify a loss function, and they even have early stopping. The network structure is not super complicated from what we have seen. The only difference is it has two different ways of getting the input. So there are two input layers instead of one. And they look at simple ways of monitoring the progress. So the point that I want to make here by looking at such real research is that you can transfer the knowledge. We talked about transfer learning, like when the model adapts to a different problems, but you can transfer the knowledge that you gain here to adapt your own problem to create your own networks too. And it's also refreshing to see, and also maybe how close real research is done through a simple Jupyter notebook. So, and this is very common in, as I understand, in machine learning and data sciences to do research and development in an interactive way, because you can track your results. You can have a narrative around it, like you can come back, you can share knowledge at the same time. So when you think about organizing deep learning, we talked about the workflow within a notebook itself, but if you're doing this such projects, eventually you will end up with collecting all your experiments documented in a notebook, and maybe even multiple documents, multiple Jupyter notebooks. So it could be very useful, but it can be also nice to sometimes think about how you're doing this. This is not a course in reproducibility or how to write modular code, but at the same time, there are some examples where you good thumb rules that you should follow if you're considering doing this. In the course itself, you might have seen that towards the end of the course, we were using more and more functions within the notebook, at least in the PyTorch ones. So this gives some amount of modularity in the code. Uh, Here also there is another suggestion to take the code itself outside of the notebook, as they had done in this chem informatics research. They build their own library for storing their models, so they know where these are, and I used Git to version control. So for code, you can do version controlling, but at the same time, since this is applied AI and data science, you need to maybe also track your experiments and the results from your experiments. So for that, we saw previously TensorFlow as a way to track your experiments. So you don't have to rely on your own workflow creating one. Another tool which is popular in academia, which although it's free for academia, I will have to say you need to pay to get this in outside of academia. But this is a very popular tool to use weights and biases for experiment tracking. So this is the larger picture. You can transform, adapt your own field. You find a workflow which works for you. And as Marlon was suggesting, you can also go shopping. You don't have to do everything from the scratch. You can look for other places for inspiration. There are a few here, maybe a bit outdated. It doesn't mention places like Hugging Face, which is increasingly popular, but at the same time, do be cautious while adapting them.